Hello, everyone. This is Patrick Hill from Triple Point. We are going to start our presentation today on the fundamentals of lagoon aeration. Thanks for joining us in our inaugural webinar. We hope to do more of these in the future. So stay posted on that going forward. So today we're going to start by having a brief introduction into Triple Point. Talk a little bit about the aeration basis of design, overview of the biological treatment modeling for lagoon systems. And then we're going to look at some aeration efficiency, compare different aeration technologies in terms of efficiency and mixing capability, look at a few case studies, and then at the end here we'll get some opportunity for question and answer period. So Triple Point. Triple Point, we have a motto around here. We call it Lagoons Do It Better. And we know this is not really the conventional wisdom for a lot of engineers and regulators. You know, they see lagoons as an antiquated technology. But what we have seen in our efforts is that lagoons are the lowest cost wastewater treatment alternative, not just from a capital point of view, but also from an operation and maintenance point of view. And that ultimately for the communities and some of the industries that have lagoon systems, they're very forgiving, they're very easy to operate, and that makes them really ideal for those environments, because the communities and the people that own lagoons don't really have the manpower system, because they are also, you know, wearing a lot of different hats: the dog catcher, the snow plow, or the guy who mows the parks, and so on. So we really feel like, definitely from a cost point of view and ease of use point of view, lagoons are no question the easiest system to operate. But also we have found that over time, in our over 100 installations, that lagoons can put out better, if not the best effluent quality that is available for any system. That's why we believe that lagoons do it better. Just before I continue here, can people send me a chat to make sure that they can hear me adequately? Is this audio working correctly? Okay, good. Okay, good. Just jump. Thanks for responding. I just had a colleague say they couldn't hear it, but I think that's on their end. So a couple of studies which kind of prove this point to us in terms of lagoons, that they can actually do it better, is CH2M Hill did a study on the Eagle Sanitary District lagoon facility in Idaho. And they looked at lots of different types of plants. They looked at SBRs, activated sludge. They looked at lots of different options for Eagle. And Eagle is in an area that's growing rapidly from an economic point of view. So, and what they actually found was that over the long run, when they penned out all the numbers and looked at all the different alternatives available to them, that the lagoons were the most cost-effective option for the Eagle Sanitary District. And so right now, they're actually in the process of upgrading that plant with some of our aeration equipment, which I'll talk a little bit about later. The second study, which I'll cite as to why lagoons do better in our mind, was done by the University of Illinois. And it looked at the different types of wastewater treatment facilities that are available. You know, again, going back to the typical ones: an SBR, an activated sludge system, an oxidation ditch, for example. And it compared each of the different technologies and looked at their capability of removing some of the microcontaminants that they're starting to study, things such as human hormones or pharmaceutical waste that are finding its way into our wastewater. And Dr. Lee Liu over there at the University of Illinois found that lagoons did the best job of actually removing those contaminants out of the wastewater. So that is lagoons really can do a good job if they're operated correctly and they have the right equipment in place. So our role as a company, as we see it, is to provide lagoons with technologies that can help them meet these new treatment limits that are being imposed upon them, or just to help them to be upgraded, rehabilitated, rejuvenated with new equipment that can help them better treat the wastewater. So, we have our Mars Lagoon Aeration system, which we've installed in lagoons for the better part of a decade plus now. We developed also our Nitrox Lagoon ammonia removal system and our Nitrox Plus D, which is a lagoon total nitrogen removal system. And then finally our Phosbox system, which helps lagoons meet a phosphorus limit. So we really aim to be a total across the board. And so we provided these technologies to help lagoons to be upgraded to meet whatever effluent requirements are needed at the back end of the plant. The second part of our mission is that we want to foster this idea that lagoons do it better. We want to change the perception of lagoons. And so we do that by holding these kinds of educational events where we have webinars, this is our first inaugural webinar in terms of we're going to plan on doing more of these going forward. But we also have informational blogs on our website, which you may have seen. We just launched our YouTube channel where we do short YouTube videos and interviews and with people that deal with lagoons a lot and try to provide tips and tricks and different understanding and education around lagoons. Also have field training events. So we just got back from Missouri and Iowa where we did 4 days of training, on-site hands-on training at lagoons, help diagnose lagoon problems, help to teach operators how to better operate their lagoons overall. And then finally, we developed a Facebook community around this concept of lagoons do it better. That we feel like if we can get this community going to the point where operators can post questions and other operators can answer those questions, that we can, operators or engineers for that matter, on both sides, bring them together. Everybody can help each other, help their lagoon operate better. And ultimately change this idea. So if you go to tpenv.com/LDIB, we have all the information about these different resources that are available. If you register there, we'll send you a free hat and a transfer stickers and paraphernalia for Lagoons Do It Better. So I encourage you to do that. We're really trying to help everybody, help all the lagoons, improve the treatment and come up with the better solutions to the problems that lagoons are seeing. So with that, I'll move into the presentation. So lagoon aeration, what's important to understand about aeration in general is the definition. What is aeration, right? And according to the EPA, the purpose of aeration is twofold. Number one is to provide the oxygen required for the metabolism for the microorganisms. They need to breathe. They need to have the oxygen required to break down the waste. And number two, and perhaps I'd say for a lot of people in the aeration field, what's more important, and I'll get into this in a little bit more detail, mixing is really, really critical in a lagoon and in any wastewater treatment process, to be honest. Anaerobic digestion, aeration, whatever it is, mixing is critical because you've got to get the microorganisms, the waste, and the oxygen all mixed up together. And the better job you do of bringing all those three elements together, the better treatment you're going to get out of the equation. So sometimes people focus, what I found is people focus too much on aeration and oxygen transfer, and they don't focus enough on this mixing portion. And if you actually read the literature and you open up Metcalfe and Eddy and you look at the EPA fact sheets in the world that talk about aeration, there's a big, big emphasis on mixing. So we're going to carry that theme through. So when we're looking at lagoon treatment overall, really its very basic form is a function of the site conditions plus the aeration, right? Which is, as I just mentioned, oxygen transfer and mixing rate, right? So this is a very, very basic formula, which probably oversimplifies it, right? But it gives you an idea of what we look at when we look to design an aeration system. We're looking at site conditions, number one, and then we're looking at the aeration, and we're saying, how much oxygen do we need and what mixing rate do we want to have in order to accomplish our end effluent result, right? To get the biological treatment that we want. So for site conditions, what we're looking for is we're looking at BOD loading, and I'll talk a little bit more about that in a second, TSS, and nitrogen on the system. These are all things that draw up oxygen. We need to know what we need to design for, right? Beyond that, we're looking at depth. Depth is important, and I'll talk a little bit about that in a minute. Total volume, and as that pertains to retention time, which means very simply, how much time is the water sitting in the lagoon? How much time do we have to treat it, right? Water temperature, or sort of the ambient temperature, is really what we look at there. The contaminant factor. Contaminant factors have to do with your wastewater. What are you dealing with? Are you dealing with municipal waste? Are you dealing with dairy waste? Are you dealing with pulp and paper waste? What kind of wastewater are you dealing with? And that makes a big impact on oxygen transfer, because ultimately, the way that oxygen is transferred to water does vary depending on what's in the water itself. And I could talk a little bit about that in a little bit. TDS factor, which is the total dissolved solids factor, is important. And then also what level of dissolved oxygen concentration you need to run in your system. So, for example, there's a lot of lagoon systems that have DO requirements at the effluent, right? So when you're designing an aeration system, you got to understand what the effluent requirements are for DO, so that you can make sure you have sufficient dissolved oxygen designed into the aeration system up front to meet that DO requirement at the end. So that's just one example of why DO is important. So I would say probably, there are two, I'm going to focus on two really, really critical factors, right, when you're designing aeration systems. One are the oxygen requirements, and the second one is the volume and general depth and retention time. So oxygen requirements are key, because what we know from looking at Metcalfe and Eddy, right? If you open up Metcalfe and Eddy, it's the wastewater Bible, right? They're going to tell you that you need 1.5 to 2 pounds of oxygen, right, per pound of BOD coming in, right? So what we will do is we will calculate your influent flow, right? You're going to tell us what your influent flow is. You're going to tell us what your influent concentration of BOD is, and we're going to convert that flow and concentration to the pounds per day, right? And then in order to determine how much oxygen we need to treat that influent BOD, we're going to take that pounds per day and times it by 1.5 or times it by 2 or whatever the factor is. We typically use 1.5 pounds of oxygen per pound of BOD coming in. But, certain people like to use 2 for conservatism's sake, and so on. So that tells us the total pounds required, right? In addition to that pounds required, we also need to put in extra oxygen level, right? And this extra oxygen is really buffer. It's not required for the biological process. We only require 1.5 pounds, but what we want to do is we want to have buffer in there to prevent odors, to make sure that we're going to keep what we call a mainly aerobic environment, right? Because as soon as things tip over into an anaerobic phase where there's not enough oxygen in there, we start to see odors because we get H2S production. We start to see a drop off in treatment because anaerobic treatment is much slower than aerobic treatment, and so on. So we really need to have anywhere between 0.5 milligram per liter to 2 to 3 milligrams per liter of dissolved oxygen, just residual in the water column. And as I mentioned before, in order to, if you have an effluent requirement for DO, we can design for 5, 6, 7 milligrams per liter DO in the water if we need to. in order to meet that effluent DO requirement. And that's just oxygen that's needed over and above what's already in your system. So that is the typical basis of design and how we design oxygen requirements. Now, if you're trying to treat ammonia through your system as well, there's a different metric for that. You need 4.6 pounds of oxygen per pound of ammonia coming in, so significantly more oxygen. And then you also need to run a higher dissolved oxygen level because of the type of bacteria that eat ammonia, that convert ammonia, that nitrify and convert that ammonia into nitrate, require just a little bit more oxygen in the water in order to do their job consistently, especially at colder temperatures. So that's typically how we're designing that oxygen requirement. It's pretty simple math. I think it's really not that complicated when you break it down, but you've got to provide enough oxygen for the bugs. If you don't provide enough oxygen for the bugs, they are not going to break down and do what you want them to do. That's really critical. The second most critical thing we look at is we really look at a lagoon from the perspective of looking at the volume in the lagoon, which means the dimensions of it, the depth of it, right? And so, again, very simple calculation. We're figuring how much water's in there because we know if it's 6 foot deep and it's 150 by 300 in terms of width, and we know that the side slope is 3-to-1 slope, right? We can calculate the volume of the water, and when we can calculate the volume of the water, we can calculate how long the water is going to be sitting there, right? And in general, the lower the retention time, the lower treatment you're going to get, and the higher effluent BOD you're going to see, right? The longer the retreatment time, the better treatment you're going to get, and the lower BOD, right? And that's just mixing kinetic, and we'll talk about mixing kinetics in a little bit. The second thing that's really important is, your depth is going to determine kind of what the best aeration is for your lagoon, right? If your lagoon is anywhere between 6 and 15 or 20 feet deep, diffusers can be a good option, and we'll talk about diffused aeration in a minute. If your lagoon is less than 6 feet deep, then maybe surface aerators are gonna be better option. And the reason for that is that bubbles need time to rise through the water column. So if you have a diffuser that's sitting on the bottom, it can take if it's 8 feet deep, by the time it gets released and rises to the surface, it's going to be in the water column a lot longer, and therefore it's going to transfer more oxygen to water relative to if it's 5 feet deep, right? And so what diffused aeration is, you end up putting in a lot of aeration diffuser equipment because you don't have as much bubble rise time, so you got to get more aerators out there. Now, it still might be more cost effective to use diffused aeration because it's going to be more efficient versus a surface aeration system. It's just a really key factor to keep in mind that depth plays a big, big role in oxygen transfer. So there are a lot of different definitions of aeration, and different terminology, and it can be quite confusing, right? So I'm not going to touch on a huge degree, but definitely some of the key ones that we use. So SOTE is a measure of the standard oxygen transfer efficiency, right? And this is a very, very often referenced number. This is probably one of the most referenced numbers when you're looking at aeration technologies, right? So what this is a measure of when that bubble gets into the water column and it starts to rise, right? How much of that bubble, how efficiently does that bubble transfer oxygen to water, right? It doesn't really deal with energy directly, and I'll talk a little bit more about that in a minute, but it's really just looking at under standard conditions, which means in a lab under ASCE testing standards, American Society of Civil Engineering testing standards, how much of that bubble transfers oxygen to water. That's what it's a measurement of. And typically when we have, when we're looking at this, we're talking about it in terms of percentage per foot, when it comes to the diffuser. So, you know, fine bubble will get about, you know, anywhere between 1.8 to 2% of oxygen transfer efficiency per foot of submergence, right? Now that does change based on depth. It does change based on, you know, the different site conditions that we talked about earlier, but it's something that's often referenced as SOTE per foot. Another reference which you'll typically see is what we call standard oxygen transfer efficiency, or standard oxygen transfer rate. And that's in terms of pounds of oxygen per horsepower hour, right? At standard conditions, which again is according to the American Society of Civil Engineers oxygen transfer standard oxygen transfer testing, right? Which outlines, you know, a whole set of conditions in which you test for oxygen transfer efficiency, right? So this is a better metric in terms of telling you how many per horsepower hour. So this connects that SOTE to the actual horsepower that you're putting out, which is what most people tend to care about. There's also AOR, which is actual oxygen required, right? So that's telling you, that's in essence, that's essentially the calculation that I showed you just before, where we're taking the number of pounds of BOD, we're timesing it by 1.5 to get the number of pounds of oxygen we need, right, to treat that BOD. And then we're saying, well, that's, you know, in a very simplistic fashion, that's our AOR, right, our actual oxygen required per basin, per lagoon, per, you know, whatever, you know, baffled section, or however you want to calculate it, right? So that's an important factor. That's just making sure we got enough oxygen required in the system. Standard oxygen required, that's to do with standard oxygens being transferred. Field transfer efficiency, and I'll touch on this equation as well. That's where we take, field transfer efficiency is where we take the standard oxygen transfer efficiency, the SOT, and we convert that into what actually is going to happen in the field. So standard oxygen transfer efficiency is done in a lab under test conditions, lab conditions, right, and clean water, right? Field transfer efficiency takes that, the field transfer efficiency equation takes that SOTE number and converts it into what we call an FTE, a field transfer efficiency. And that's a really critical step. We'll talk a little bit about that. And then standard SCFM is standard cubic feet per minute. And so that's just the airflow, right? So when we're calculating we're taking the AOR, we're also taking the SOTE, converting that into a field transfer efficiency equation using the field transfer efficiency equation, and that's telling us how many SCFM we need, right? SCFM is obviously going to determine the amount of horsepower you need to push that volume of air into the water column. And then also, like I said, ASCE refers to more generally the American Society of Civil Engineers and their testing standards. So typically what you're going to see is that when you're comparing different aeration systems, they should have some level of testing done on them. If they don't have any testing under ASCE conditions, then essentially there's no way to verify their oxygen transfer efficiency, right? And so what the testing standard does for engineers and for manufacturers, for that matter, that use it, it gives them a baseline to be able to say, we know in clean water we can do this at this depth, right? We can transfer 2% per foot at this depth. And we know we can apply this field transfer efficiency equation to convert that clean water number into a wastewater number. And then we can take that wastewater efficiency and then figure out how much oxygen or how much SCFM we need to put that oxygen in the water. If you don't have that, if you don't have that clean water number to begin with, you're basically making it up. And there's a lot of companies out there, not a lot, but there's a number of companies out there that don't have clean water oxygen transfer testing done under ASCE conditions, and they are literally just making up what they think their system can transfer oxygen to water. And it's not a very scientific approach. And more often than not, they undersize the aeration system, don't put enough oxygen or horsepower out there to get the job done, because they never actually went through the testing to figure out what their system can transfer oxygen to water. So as you look at different systems, I think one of the first things you got to ask any manufacturer that you're looking at is, where's your testing? You know, it's kind of like when you're buying a used car. Where's the Carfax, as they say? Well, where's your testing, right? Because if they don't have any testing, they're just making it up. And if they're just making it up, chances are it's not going to work. So as we look at aeration, you know, as I mentioned, you know, you have standard oxygen transfer efficiency, SOT, as sometimes it's called. But really, in reality, that really doesn't matter as much as horsepower required to put the oxygen in the water. And the reason we care about horsepower, right? We care about horsepower because horsepower determines how much energy is used, right? How much energy is used makes up over 50% of a wastewater treatment plant's energy consumption. It's typically done on aeration. So if we can make our aeration system more efficient and use less energy, we can save money, and oftentimes we can underwrite any aeration system, the cost of any aeration upgrade, by just simply by the energy savings that are attained through that system. So that's why we care, right? We don't really care about SOTE per se. We care about the energy required to accomplish that oxygen transfer, right, in most cases. So when we look at this, it's really important to know that SOTE does not equal energy efficiency. And I say this because sometimes I run into situations where customers or engineers are looking at different technologies and they're just comparing SOTE. They're not comparing anything else, right? And they're not looking at what the actual horsepower requirements are. They're just saying, oh no, this is the SOTE. This guy's higher than, this technology is higher than that technology. Therefore, they're more efficient, which isn't actually true from an energy point of view in some cases. SOTE is a function, energy consumption is a function of SOTE and back pressure in large part. So this is a very simplistic way to look at it, right? Which is, if you have a high standard oxygen transfer efficiency and low pressure, you're going to get the best, lowest brake horsepower in the system, right? Which is going to lead to the least amount of energy usage. On the flip side, if you've got high SOTE but high pressure, then you're not going to be particularly efficient, right? Or you're not going to be as efficient in some cases as somebody with a lower back pressure. So it's really important to look at the interplay between pressure and SOTE and understand that ultimately SOTE is not a universal metric for energy efficiency. It really comes down to back pressure. So to give you an example, there are a lot of, in the mechanical plant world, there are things called panel diffusers. And panel diffusers tend to be fairly high, right, in SOTE. And they are because they create very small bubbles, right? And the smaller the bubble, the more collective surface area you have, therefore the more oxygen you can transfer to water. And you also, but smaller bubbles are less buoyant, so they sit in the water column longer, which gives them more of an opportunity to transfer oxygen to water. And there's probably 4 or 5 other reasons why smaller bubbles are more efficient at transferring oxygen to water. But with some of these panel diffusers, the first, when they came out, it was fine. They actually looked at the pressure that was needed to force the air through the smaller orifices that created smaller bubbles. They actually found that they were less efficient, or they were about the same efficiency or only marginally better, but cost twice as much from a capital point of view. So I think they've improved them over time, no question, but that gives you an example of, if you looked at SOTE alone and didn't look at back pressure and how that relates to horsepower requirement, you would never, really get a good understanding of what the true energy efficiency of the technology is. You would just blindly be looking at SOTE and say, wow, they can get 3% per foot. Well, of course they're going to be more energy efficient, when in fact they're not, right? If there's a higher back pressure, they could use up to 25% more horsepower than a system that had lower back pressure but had lower standard oxygen transfer efficiency. So it's really important to keep that in mind. So what we look at, and what I'll be sort of touching on in this presentation, is what's called standard aeration efficiency. And it's another way of saying SOTR, which is standard oxygen transfer rate, right? And this is a measurement. This is a true measurement of energy efficiency of an aeration system. It is the measurement of pounds of oxygen, right, per horsepower hour that you can put in the water, right? And that's what you care about, right? You care about how many horsepower is going to require me to put the oxygen in the water. So what determines that are SOTE and back pressure, right? They're big factors in this. You know, if you have, again, going back to the last slide, if you've got high SOTE and high back pressure, then it's going to require more horsepower. If you have lower SOTE but lower back pressure, it might be roughly the same. And then it comes down to taking that SOTE, using the field transfer efficiency equation to calculate what the SCFM that's required, and then it's SCFM and back pressure which determine ultimately what the standard aeration efficiency is, right? So SOTE gets converted into SCFM using the field transfer efficiency equation. Then you're looking at the total airflow of that SCFM plus the back pressure, right? Determines horsepower requirement and ultimately brake horsepower requirement for energy in the system. So that's the basic interplay of what's happening here. And it's a little bit complicated because it's almost circular in a sense, but it does start from one thing to the next. So when we look at SAE and compare the different aeration technologies, I'm going to go into each one of these different systems individually and give a little overview of them, and then I'm going to show you a couple case studies, right? But we don't talk about standard oxygen transfer efficiency at this stage because we care about energy. And so what we're looking at is the number of pounds of O2 per horsepower hour, right? So this table shows you the basic technologies that you typically see with lagoon aeration systems. And this is done, this was put together by the only independent testing facility in the United States, which is out of Nashville. And so these guys at GSCE do literally thousands of tests a year on different aeration systems. And aeration systems into certain categories. And then they created this table and said, okay, well, how do these different technologies on balance? I mean, they're not looking at any one manufacturer, they're looking at a number of manufacturers. How do they stack up from an aeration point of view in terms of SAE, standard aeration efficiency? So at the top, you've got fine bubble membranes, and this is really pertaining to EPDM or some kind of fine bubble membrane material, which could be silicon, could be polyurethane, could be EPDM, but in general, it's something of that realm. It doesn't really look at, this fine bubble membranes is not looking at ceramic fine bubble diffusers, which are used in aeration tanks, not so much in lagoons, or a static orifice fine bubble diffuser, which I'm not going to get into in this too much into this in this presentation, which is another dealing with membrane diffusers. Our Mars system is right along the same efficiency at 4 to 7 pounds of oxygen per horsepower hour as just general fine bubble. Then you've got coarse bubble static tubes, which you find in lagoon systems. They get a little bit less efficiency, about half that of a fine bubble system. And then finally, surface aeration. And again, this includes a range of 1.5 to 2.25 pounds of oxygen per horsepower hour, depending on what kind of area, a surface area you're looking at. There are a number of different types of surface aerator, but this is just them kind of classing it together, more or less, in terms of their testing. So when we take that and put it onto a graph, what we see is the sort of fairly decent stark differences between the oxygen transfer efficiency of a flammable system system. You're typically going to see a fine bubble system operate at about 50%, 50 to 60% more efficiently from a horsepower point of view than as compared to a coarse bubble or surface aeration system. And this, in large part, is why a lot of the aeration that gets put in, a lot of new upgrades that happen with lagoons, typically involves fine bubble a lot of the time, because of these big differences in terms of efficiency, but also in terms of maintenance, which I'll talk a little bit about. So the two primary equations that we will use in terms of calculating lagoon aeration is going to be the field transfer efficiency equation and the biological treatment efficiency equation. So I'll start with the field transfer efficiency. And as I mentioned earlier, what the RTE number, right, the standard oxygen transfer efficiency, which is done in clean water at a lab, right, under the American Society of Civil Engineers testing standards, right, and it's to convert that into a field number, right? So that is saying we're going to take this from the clean water. What's it going to do when it actually gets into your wastewater? Because obviously there's a big difference between wastewater and clean water. So one of the biggest parts of this equation is what's called the alpha factor, right? Or the contaminant factor. So that's saying that based on clean water, when we put it in the field, there's certain things in wastewater that are going to stop that bubble from transferring oxygen to water efficiently. Okay? So for example, if you have a lot of fats, oil, and greases, or certain types of fat, oils, and greases build up on the surface of the bubble as it rises through the water column, right? And as they build up on the surface of that bubble, they'll actually inhibit some of the oxygen transfer that's occurring in that bubble. And it depends on the different fats, oil, and greases you've got in your system, but that's just to give you an example of what can happen. And so what this alpha factor does is it basically derates the lab number into a more of a realistic field number, right? And so this changes really based on your wastewater, right? And from a municipal point of view, if you're designing for a municipal plant, we, with a fine bubble diffuser, we will typically use an alpha of 0.6, but you can use alpha factors of anywhere between 0.4, which would be really, really derating the oxygen transfer efficiency in clean, 0.4 in a really caustic environment like, pulp and paper, or some kind of really nasty chemical processing plant or something like that, all the way up to 0.7, which we don't use 0.7, but you could in a municipal setting where it's the water obviously has its wastewater, but it's not dealing with particularly bad contaminants, and the pH is relatively adjusted, things like that. So what happens when you apply this equation is you end up making an assumption, right? We assume that the alpha factor is going to be 0.6 in a municipal setting, but and municipal is okay because we can test site to site, and wastewaters tend to be relatively homogeneous. But when you get to an industrial setting, it really we're basically research in the field and taking an educated approach to it and saying, hey, we know from this research paper that alpha factors for dairy wastewater are 0.5 or they might be 0.6, or for pulp and paper are 0.45, for example. And so we're going to look at that. But if we really wanted to know, you would need to do a specific test on the wastewater, an alpha factor test on the wastewater that we're dealing with, in order to really know what the alpha factor is. But generally speaking, it's assumed. The TDS factor, typically, that's going to be 0.9 to 1. It doesn't change a whole lot based on the wastewater, but it's based on the total dissolved solids that are in the wastewater. Temperature plays a role in oxygen transfer efficiency. Typically, when it's colder, you get better oxygen transfer efficiency than when it's warmer. You've got target dissolved oxygen level is another factor. So with target dissolved oxygen levels, that's the buffer that we talked about. That's the 0.5 to 3 milligrams per liter of additional oxygen that we want to keep around the water column, or that's the 6 milligrams per liter of oxygen you need for your effluent requirement for DO on the discharge. That's where that number comes into play, which is we add that into the equation here, right, to take our lab SOTE, and then we say, okay, we need this buffer of oxygen in the water column too. So that'll factor into this equation. Saturation concentration rate, saturation oxygen concentration at standard conditions. These are typically standard numbers that are plugged in based on research, and then water temperature in degrees Celsius also plays a factor as well. So all these things put together in this field transfer efficiency equation, this is on every one of our basis design has this equation on it. We use it to determine what the field transfer efficiency is we're going to achieve at different applications, so that we can ultimately determine the amount of SCFM. Once we determine the SCFM, we can then say, okay, well, what's the biological treatment going to be through the system, right? Because anything in any aerobic system, we are assuming in our biological treatment efficiency equation here that we are getting the sufficient pounds of oxygen in the water. So it's just assumed in this biological treatment efficiency equation that we're getting the oxygen we need in the water. So really the biological treatment efficiency then becomes a factor of the kinetic rate, right, and the treatment time, right? And we talked about retention time and how important that is, right? Most cases, we're coming into lagoons that are already there. So we're just plugging that treatment time into the equation. We're calculating the volume of the lagoon. We're calculating the flow rate. We're saying how long is this, this water sitting in here. And typically it's, 20 to 25 days, maybe 30 days of retention time in a typical lagoon system. And so that's getting plugged into this equation. Then we look at the kinetic coefficient. Now the kinetic coefficient, this is where mixing comes into play. The kinetic coefficient is largely dependent on the level of mixing within the system, right? So that is why mixing is so critical in aeration, right? Because the higher mixed we are, the better kinetic coefficient we get, the better treatment we get, the more treatment we can accomplish in a smaller footprint, right? So, and the reason for this is very simple. Again, it goes back to that idea of mixing, of getting the oxygen that's in the water, the bacteria, and the food together. And the better we do that, right, the more treatment we're going to get out of the system, the more active the bugs are going to be, the more BOD they can consume, and ultimately, the better effluent quality we can achieve, right? So if we look at this and we look at the different treatment kinetics, and we typically use these 4 different treatment kinetics in our calculations. You've got partial mix, and this is what most lagoons, aerated lagoons are within a municipal setting, and even in an industrial setting, or what we call partial mix, right? Partial mix means you're not getting complete mix, and you're getting largely aerobic, but you are getting some anaerobic digestion as well, because you're, by definition, going to allow some solids to settle in a partial mix environment. Then you go up from that to what we call vigorous mix, which is a little bit more mixing than partial mix. You're keeping more active, bacteria and waste in the water column. You're getting it up in there. Therefore, you're getting a little bit better treatment kinetics. Then you've got, from there, you go to complete mix, right? Which is just where you're really getting what we call a complete mix environment. It's really rocking and rolling on the surface. You can see the, bubbles are everywhere. You can see the pattern. You can see it keeping everything up in suspension where it can be mixed. And then finally, the top of that is what we call complete mix return activated sludge, right? So that's where we're not only just feeding the water into the lagoon and just aerating it, right, and completely mixing that lagoon. We're also completely mixing that lagoon, going into some kind of solid separation, clarifier, DAF, and then we're recirculating solids, right, from that area, which include BOD, which include, so basically we're including bugs and food, and then we're taking those solids and we're putting back into the lagoon. And what that does is that creates a flock, right? Which, in addition to a complete mixed environment, means that we're just super hyper concentrating that bacteria right into the lagoon, and that's when you get more bugs, you get more treatment. So what this means from an aeration point of view is, the different levels of mixing for a diffuse system are going to be largely dependent upon the amount of air you're putting into the system. So this comes from Metcalfe and Eddy. If you're looking at complete mix, for example, Metcalfe and Eddy, pull open the book, you turn to the chapter on mixing. The definition of complete mix for Metcalfe and Eddy is anywhere between 10 and 25 SCFM per 1,000 cubic feet of water in the lagoon, right? So, if you're complete mix RAS, you might want to have 15 to 25 CFM per 1,000 cubic feet. If you're just complete mix with the lagoon as it is, then it's 10 to 15 CFM per 1,000 cubic feet. If you want vigorous mix, it's roughly 8 CFM per 1,000 cubic feet of water. And then partial mix, is typically 2 to 5 SCFM per 1,000 cubic feet of water, right? So that, in a general sense, that's the typical design for mixing. And that determines the level of treatment you're going to get within the lagoons. And obviously, it also determines the amount of aeration equipment you need within the lagoon. If you're going to complete mix the system, you've got to put in a lot more diffusers to get that airflow out there, right? Relative to a partial mix, where you're going to put a lot fewer in to get that airflow out there. And so it really, how much retention time do you have? How much mixing do you need? How much oxygen do you need to get the job done, right? And we're going to look at that and determine what the level is. What we do is we look at that and determine what the level of treatment you need and then make a recommendation based on that. So we're going to look at 3 different aeration technologies: surface aeration, fine bubble diffusion, and then also our Mars system. I did mention coarse bubble previously in my breakdown of different efficiencies. I'm not going to dwell on coarse bubble for lagoon systems because I'm actually not aware of a manufacturer that sells coarse bubble aeration for lagoons, and I think that's in large part because it's been supplanted by fine bubble diffusion, where most people now realize they can get the mixing out of fine bubble, and they get way better oxygen transfer, so they don't really use coarse bubble anymore. So I'm not going to dwell on that too much in this presentation. I'm just going to look at surface aeration and fine bubble. And those are typically what you see with lagoons in the field. So before I start this, I'm going to evaluate each of these technologies on the basis of their ability to transfer oxygen to water and their ability to provide mixing, because that is the definition of aeration, right? So we're talking about the fundamentals of lagoon aeration here. Those are the 2 things that are big takeaways, right? Is that the fundamentals of lagoon aeration is you got to get oxygen to water and you got to keep it mixed. And if you do those 2 things, right, you're going to get better treatment, right? Or you're going to get the best treatment, depending on how well you do those things. So I'll start with our system. We have our Mars aeration system between a fine bubble EPDM membrane diffuser plus a coarse bubble static tube. And so what we're doing here is we're harnessing the efficiency of a fine bubble system, right? And then we're incorporating the mixing capability of a coarse bubble static tube system. And so what that allows us to do is accomplish both that definition of aeration of adding oxygen to water and keeping things adequately mixed within the water column. And the third part of the system, which is really important, is that it's a portable unit. So it's actually designed to be retrofitted into an existing lagoon without taking it offline, without dewatering it if you don't want to, and instantly upgrade your aeration system within a matter of days. So typically how we lay this out is we will have a blower over here on the left-hand side of the screen, right? And a header underneath the ground that'll come up to these manifold points, which, if you can see my mouse, are there. And these manifolds have ports on them for each individual aeration unit that are connected to them, right? And each port has an air line, which is going out to each unit in the field. So when you're installing this, you're basically connecting one side to the manifold, connecting the other side to the aerator, taking it out in a boat, dropping it down, and it's literally sinking by its own weight and sitting on the bottom. And then you're turning the air on, and it's just diffusing and mixing and aerating right there in place. So as you see here, you've got the fine bubbles on the outside. Lots and lots of thousands and millions of fine bubbles are being diffused, which are transferring oxygen to water. And then in the circulating water, it's creating an airlift type effect where it's pulling water from underneath the unit and pushing it towards the surface. And that's creating circulation and mixing. Circulation is important because it's actually going to pull some of the liquefied sludge that might be sitting on the bottom previously, and it's going to put it in the water column where it can be mixed and broken down and actually add oxygen to that, where the bugs can get in contact with the food and the oxygen required, right? And so what we found with this capability is that we can actually reduce the level of sludge on the bottom of a lagoon up to 50% of the volatile solid component of that sludge we can actually break down. And what that means is, of the stuff that can be broken down, of the organic matter that comprises your sludge blanket, we can actually break that down about 50% of that, 40 to 50% of that. So it can be a really, really good solution for lagoons with lots of sludge in them. Lots of organic sludge, I should say, in them. So it really does do a good job of mixing if there's one thing it does. So what this installation profiles allows you to do is it really does allow you a lot of control and ease of maintenance and ease of operation of the system. And ultimately, it tends to be more efficient than a surface aeration system by about 60%. And it's also lower maintenance than the surface aerator system because instead of having 8 or 10 motors on the water, for example, you've got 1 to 2 motors sitting on shore, which are your blower units, which are feeding the air to the units out in the water. So you've got fewer motors to maintain, and the motors you do have to maintain are much, much simpler. And that's another reason why the market tends to be shifting towards diffused aeration as opposed to, you don't have, when you got a surface aerator sitting on a lagoon, you ultimately have to go out there and pull it in and, maintain it, lubricate the bearing and so forth. Where with the Mars system, with the blower sitting there, you can access them a lot easier. That's what it comes down to. So, as that compares to surface aeration, there are several different types of surface aerators. So this is what they would call more of like a jet surface aerator. You can see in this picture. This is what they call more of like people call it like a splasher or a donut style aerator, or and more generally speaking, it's just a vertical surface aeration system. Typically is sort of more of the technical name for it. And then you also see what are called aspirators. And aspirators are they're really a combination between a directional mixer with a propeller on the end of it, plus what they do sometimes is they'll put a regenerative blower on the unit and actually push air down the shaft that then gets broken up on the other end and creates sort of semi-medium to fine bubbles for the system. and just create a lot of aeration that way. So generally speaking, I call surface aerators in a general sense they're sitting on the surface, right? And you do get different efficiencies depending on whether you're dealing with a jet, a splasher, or an aspirator. But they do tend to stay roughly within those ranges of 1.5 pounds of oxygen to 2.25, 3 pounds of oxygen per horsepower hour. But generally speaking, that's where they sit. In general, I'd say the pros are that they're very portable. You can float them out there. They're very modular. If you just want one aerator, you can chuck an aerator out there. It's pretty easy. I say chuck it out there. It's harder than it sounds, than I'm making it sound, but it's possible. They're good for like pulp and paper uses a lot of surface aerators. And one of the reasons for that is that, pulp and paper has a very caustic waste stream. The water is really nasty stuff. So if you use a fine mobile diffuser, oftentimes it can get plugged up relatively easily within that environment. And so it doesn't actually do any, it's not going to perform, you're not going to get the oxygen transfer efficiency out of the system if it's plugged up. Now, I think those applications for really pulp and paper is really the only one that comes to mind. But ultimately, fine mobile is going to be better in 90% of the applications that are out there. But there is that benefit of a surface aerator that it just doesn't care as much what kind of wastewater that it's in, because it's more mechanical in nature than it is, diffuser in nature, in terms of transferring oxygen to water. Surface aerators are also quite good at shallower applications. Like I said, depth plays a big role in oxygen transfer efficiency. So if you're trying to aerate 6 feet of water, you really have a hard time you have to put a lot of equipment for diffusers in the field in order to aerate that water, get enough oxygen in the water, where surface aerators are going to be less affected by that depth variation because they're sitting on the surface. They don't really care what the depth is, So there's certainly some applications for surface aerators, but like I said, I think aeration efficiency that surface aerators get, there's a big tendency and overwhelming trend that I find in the market where most lagoon aeration upgrades, if the lagoon's over 6 feet deep, they're going with some kind of diffuser. And this is largely due to efficiency, but also maintenance as well. I can't tell you how many times I've been to a lagoon facility that has surface aerators and seen a boneyard of surface aerators just sitting on the shore, not in service because they're not, they're just shot. They can't be fixed, and they don't have money in the budget to put new ones out there, or whatever the case may be. So, they're a big maintenance nightmare. Lots of motors out there, lots of motors on the water. Regular maintenance. The maintenance is difficult because they're on the water, and it's, invariably, it's hazardous being out there, to fix these things. Nobody wants to get it's broken at some point because they're not maintained. Is what it comes down to. So those are the big issues we see. As I said, going back to the oxygen transfer efficiency, typically when you compare a surface aerator to a fine mobile diffuser, a MARS unit included, you're going to get about 60% energy benefit by using a MARS system, fine mobile relative to a surface aerator. And then when we compare the mixing capability, I think, again, when you get above 6 feet of the water column, I think surface aerators are inherently going to have a difficulty mixing that water column. So if you can see in this diagram on the screen on the right hand side, I show the surface aerator here, the sort of an aspirator type, and it's going to mix about the first 6 feet of water column. Below that, it's going to have a hard time. There are going to be dead zones down here and around where the unit is, where it's not right. And mixing is important. Going back to it, it determines the level of treatment that you get within a lagoon. It also determines the level of sludge buildup that you see within a lagoon. So if you have surface aerators, you're way more likely to build up sludge than if you just have, like a MARS system or a diffuse system. So that in comparison to our MARS unit actually sits on the bottom. So it's actually going to be mixing from the bottom to the top, right? So in addition to being more efficient, you tend to get better mixing, which means you get lower sludge buildup, or you can keep more of those volatile solids in the water column so they can be broken down, and ultimately you should get better treatment through the system in addition, because you're just getting better mixing across the board. So this is a funny quote. Actually, it's not from us. Actually, it's actually a quote from a guy who runs the independent testing facility in Nashville, Arkansas, where a lot of the oxygen transfer efficiency testing is done in this country. And he said to us, he's worked with aeration for years. He has, used to work for a company that made surface aerators. He's now a consultant. And so he has lots of experience. And he said, surface aerators are a self-destructing piece of equipment. And I'd say that's probably the biggest reason why there's sort of a trend away from surface aeration within the lagoon aeration field, is that they have lots of maintenance issues. So the next system that we're going to look at comparison would be to fine bubble. Now, like I said, I think fine bubble is really where the industry is going in terms of the reason for that is mainly due to the high efficiencies that you see and just lower energy that's required. The other thing is the maintenance is overall probably a little bit easier, just because your main moving part in a fine bubble system is going to be your blowers, which are sitting on shore. And those are the items that are going to require the most maintenance on a regular basis. So they're just way easier to access, and there's just fewer motors to maintain. So that's why you see it. Now you do need to maintain fine bubble diffusers, and they will over time get a buildup of what we call biological fouling or chemical fouling, which will occur on the surface of the membrane, which will need to be cleaned off at some point, which means pulling them up and maintaining them. But that's really depending on whether you're or it depends on your concentration of waste as to how often you need to do that, right? If you're an industry, you need to do that maybe once every 1 to 2 years. If you're a municipality, you may only need to do it once every 5 years or so. And that's really just one foul swoop. You're getting out there, you're doing it, you're getting it done. So it does tend to be the preferred approach. Now, fine bubble only, if you're just putting fine bubble diffusers in lagoons, what we have found in our experience, and part of the reason we developed the MARS system, was that really, you can see here from this diagram on the right, fine bubble diffusers are really not designed to create a whole lot of mixing if they're spaced out a lot, right? So when you design, a mechanical plant and you have an aeration tank in it, when one does that, there's that aeration tank with fine bubble diffusers. And that's how they're able to get the mixing that they need, right, within it to get the best treatment kinetics they can. Well, lagoons are big, right? And there's no way you're going to blanket the floor of a lagoon with fine bubble diffusers. And so you end up having to space them out from each other in a much less density than you see in the tank. And really, fine bubbles, when they developed the fine bubble diffuser, they were really looking at tanks. They weren't thinking about lagoons. Just a technology that got utilized for lagoons later once they realized they could get better oxygen transfer efficiency out of them. But the problem that leads to is that fine bubbles by themselves have no ability to mix below where the diffusion level is. So as you can see here, you got your fine bubble diffuser here. It's gonna rise through the water column, which is gonna help pull water up for sure, but it's not gonna pull any water from underneath it because there's no laminar flow to pull water upwards, right? So a typical fine bubble diffuser is gonna be positioned about 12 inches above the floor of the lagoon, or maybe even higher than that, 16 inches above the floor of the lagoon. Anything below that point isn't going to get mixed, and you're going to get sludge buildup at that point. And so your lack of mixing is going to limit the amount of treatment you can do, but your lack of mixing is also going to create sludge buildup. So again, as you're comparing that to a Mars unit here, you're really looking at a system that we can actually have that static tube in place where it can actually pull water from underneath the unit and push it towards the surface on a continuous basis, while in addition adding those flammables to water, so you're really getting that mixing plus the oxygen transfer that you need. So with that, and the efficiency for a flammable system must be. So with that, I'm going to briefly go through a couple of case studies here. We've got about 25 minutes left, and I want to leave some time for some Q&A at the end here. So I'll breeze through a couple case studies. So this will give you an understanding of how a typical lagoon upgrade goes and what it kind of means. So the city of Parsons in West Virginia was sort of the typical lagoon system that we see. 400,000 gallon a day average daily flow, aerated lagoon, built, late 80s, early 90s. By the time we got there, had been, online for 20 years. So really kind of at that point where it needed an upgrade, right? And their existing technology were surface aerators, and only about 5 out of the 8 were actually working. And so because they didn't have the oxygen in the water, they were seeing a lot of they're out of compliance on their BOD and TSS. BODs and TSSs on the back end of the system. In addition to that, they were spending a lot of money just maintaining their surface aerators. They're constantly having to pull them in, change out motors, that kind of thing. Because I think in part, to be fair to the surface aerators, they were old and they've been there for a really long time. And also in part due to the nature of the equipment. It's a self-destructing piece of equipment. So they were just constantly malfunctioning and having to stay on top of that. And eventually they just couldn't afford to keep on top of it. So that's kind of ultimately what led to their situation. Now, as I mentioned earlier, they're looking at the Mars system and they're saying, well, wow, we can get 60% energy efficiency by switching from the Mars, from surface aeration to the Mars system. This looks like a good idea. And then on top of that, they were like, wow, well, we can get better mixing out of this, just like I talked about. You don't have these dead zones that their current surface aeration system with their 8 feet of lagoon depth are seeing. We're mixing the entire water column. So it really does creating a better mixing from a vertical point of view, in addition to a horizontal point of view, which I'll get onto in a minute. So it was really quite a struggle for them to maintain their surface aeration system. Just shows you some of the surface aerators that they were dealing with. This particular one here was malfunctioning, one of the splashers. So they had both splashers and the aspirators within their system. And from there, they switched to our Mars units. So they've got 18 Mars units out in the field here. Their blowers sit up here on the shore, a very short header with these different manifold points off the header, and then the airlines going out to each Mars unit in the lagoon itself. On shore, 1 duty, 1 standby. And as you can see here, I talk about vertical mixing in my previous slides, but look at the horizontal mixing. Instead of having 8 surface aerators with 8 points of mixing, now they've got 18 or 16 Mars units with 16 different points of mixing. So over double the amount of mixing from a horizontal point of view. From a horizontal point of view relative to also in addition to the vertical mixing that they're seeing. So this is some pictures of the system that's being put in place. Frank, the operator, he actually retired last year. Good guy. System, you can see the manifolds down here with the aerators out in the field here. Much better from an algae point of view as well. So as you can see, the BOD, as soon as we put the Mars system in, the BOD just literally dropped almost within a couple of days, from effluents in the 60, 50, 60, 70 range down to effluents under their 30 milligrams per liter limit within the system. Actually, I think their limit was actually 40 milligrams per liter. within the system. So you can see that the treatment was much better through it. In addition to the better treatment, they saw much better aeration efficiency and just overall savings in terms of their aeration and maintenance. So when you project out what they were spending on energy, O&M, operation and maintenance over the period of time versus what they were able to start spending with the Mars system, they were really able to see a pretty significant saving. In comparison to replacing the system, their surface aerators with new surface aerators, the Mars units paid for themselves within 2 to 3 years of being installed. So ultimately, over the life cycle, it's actually just over 2 years, was the 2.5 years was the payoff. You can see that the savings across the system by putting a Mars system in was just so much, very significant for them, where they were very interested in that. So, overall, this kind of ran home the point that, diffused aeration, like a Mars unit, is going to do a much better job of transferring oxygen to water with less horsepower. The mixing is going to get better through the system as well, which is going to lead to better treatment and ultimately help to minimize sludge buildup over the period of time. And then finally, just the maintenance from a regular point of view is going to be much less with a Mars aeration system like what they had. So I'll briefly touch on the city of Coopersville. I'll probably breeze through this because we've only got about 15 minutes left. City of Coopersville, and this is kind of on the other extreme, they had a 2.1 MGD lagoon system, which is quite big, but when we got there, that was actually lower than that. It was like 700,000 gallons a day. And they needed to upgrade the plant because they had a dairy coming into town. So they were going to go from having design loading of 700,000 gallons a day at 200 milligrams per liter influent BOD to 2.1 MGD with an average influent of 2,500 milligrams per liter BOD. So they had to get significantly more BOD in the same footprint that they already had. And so their existing lagoon really wasn't going to work for that. So what they did was they actually upgraded the lagoon to an activated sludge process, right? And so they created kind of like a lagoon activated sludge hybrid. So going back to the treatment kinetics slide, we talked about, going from partial mix being the lowest treatment kinetic for aerated lagoons, going all the way up to return activated sludge complete mix. They were on that high end, really trying to push as much BOD through the lagoon that they could possibly do to do it. What they looked at with this was just a purely fine bubble EPDM membrane diffuser system. And this is very typical. You can see this, 1 or 2 companies sell similar systems to this. Good oxygen transfer efficiency. However, like I mentioned before, EPDM is not going to do as good of a job by itself of mixing the water column. System, you end up needing way more diffuser units than you do with, say, a Mars system. And I'll explain that in a minute. So a typical EPDM system will run using what's called a floating lateral. So they'll actually float the lateral on the surface of the water, and then the diffuser will actually hang off that lateral down the water column here. Okay, very typical approach. Sometimes we will design floating laterals into our systems when we cannot dewater the lagoon to install the aeration system, and we need a lot of air in a very confined area, such as in a return activated sludge scenario like this. However, floating laterals have some disadvantages. They are subject to the elements. They tend to have the tendency in the wintertime to expand and contract and actually snake due to outside ambient temperatures being colder than the air in the pipe. They also, with diffusers actually breaking off the lateral connection if you've got inclement weather. So in general, they can be used, and they're more successfully, I'd say, in the south than in the north, but they do have issues in terms of being exposed to the elements overall. In this application, we were lucky enough that they were going to drain the lagoons. So they were going to drain the lagoon anyway to desludge it. So they actually decided to put a fixed header in place where they actually have the header fixed to the bottom. And this is a much, much more solid approach if you can do it, which because our Mars unit actually sits on the floor of the lagoon, we were able to do this relative to the fine bubble system, which was way less able to do it. And so we have our header pipe here with the tubing connected to it with enough slack on this tubing so they can actually when they need to maintain it. So it really did create a much more solid approach. Another thing with the fine bubble technology is the airflow for a fine bubble diffuser unit is much, much lower than, say, our Mars system. And in part because they've got to get the mixing through this system. So you can see here that this is a very dense aeration profile, almost blanketing the floor of this lagoon, these two lagoons with fine bubble diffusers. 900 diffuser racks with 44 laterals. With the Mars design, they were able to get away with 420 Mars diffusers with 460 laterals and get the same mixing and the same oxygen transfer through the system. So really a lot fewer units to maintain, a lot fewer laterals to install, much, much simpler overall installation for the system. So ultimately what this translated to them was much, much lower yearly maintenance costs. We didn't factor into our cost comparisons the idea that, you know, the fine bubble wouldn't do as good of a job mixing the sludge as our Mars unit. But at the same time, I mean, it's difficult for us to predict that since we don't actually know what their system won't do, what a fine bubble system won't do as well. So we just looked at purely O&M costs from the point of view of you've got fewer diffuser units. So certainly there was an operational benefit over the course of 20 years. You're going to see a very distinct benefit with the Mars system. The capital costs were basically the same, if not a little bit less for the Mars system. So it was a much, much better approach to go with Mars, where it's going to get better treatment overall, better mixing overall. With that, I will open up to questions. I see a couple questions already pop up here in my chat bar, but if you want to add questions to the chat bar, I will try to see if I can get through as many of those questions as I can in the next 10 minutes. So the first question I got here was from Ray Sprague, was discussing the sludge reduction versus alternative aeration systems within lagoons. So when it comes to sludge reduction, what you got to understand is that lagoons have different sludge composition. So if a typical lagoon system, there's two different components to sludge. You've got the non-volatile, non-organic sand, grit, things that are not going to break down, right? And in an activated sludge process, typically what they have is they have what's called grit removal, right? And that's actually taking lagoons don't have grit removal, so that grit ends up finding its way into the lagoon. Now, this is not stuff you're going to break down, right? It's just it's non-volatile, it's non-organic, so it's not going to break down. And then the other component to the sludge is volatile sludge, okay? And so in order to know what you can remove, right, you have to take samples of that sludge. You've got to measure the depth of it, and then you've got to take core samples, and you've got to get those core samples analyzed, right? And you can do a volatile solids on any core sample. It's actually a relatively inexpensive test, and it'll tell you what percentage of those solids that are sitting on the bottom of your lagoon can actually be broken down. Now, of those volatiles, you know, we are very confident we can break down 40 to 50%. But again, it comes down to the level of mixing that you provide, okay? You can't put into a lagoon and say, oh yeah, we'll get 50% volatile solids reduction. Maybe we will in that relative area, but if we don't create enough mixing, we're not going to see that, right? So when we design a system to help in part to clean up sludge, we're looking at that mixing profile, and we're looking at the spacing of the units, and we're saying, okay, what's the spacing we need based on the depth of the lagoon in order to get adequate mixing, right? So I think there's a lot of companies out there that advertise, oh, we can break down lagoon sludge, and whether it's a bacteria company, an aeration system company, whatever it is. The fact is, if they're not asking the question, how much volatile solids do you have in your lagoon? And if they're not getting that analyzed, they're making it up because they don't know. If your sludge is 90% non-volatile solids, if your sludge is 90% sand and grit, it's not going to break down. You can aerate that all you want. It ain't going to break down, right? And I'm dealing with a customer right now, actually, that asked me that exact question. Can we put your Mars units in here to break down sludge? The first question I asked him is, get a core sample done. Get multiple core samples done. He went back, did that, came back. Turns out his sludge is 90% sand and grit. Well, I'm sorry, but I can't treat that. Nobody can treat that. So I think our Mars system, I believe it'll do a better job breaking down sludge than any other system due to this mixing component, due to the fact that we're sitting on the bottom, and due to the fact that we're circulating the water column from the bottom to the top, and due to the fact that we're going to put more diffusers in than any surface-related system will, and spread that mixing energy out across the bottom of the lagoon system. So ultimately, I think that we give ourselves the best chance of doing that. But I think that's how we compare. Okay, I got a question here discussing the nuance of odors. If there's lagoon sludge buildup with the Mars system. So odors are as a result of volatile sludge breaking down anaerobically, right? The anaerobic digestion that's occurring on the bottom of your lagoon, right, is creating H2S, which is then bubbling up to the surface and getting released into the atmosphere. When you install a Mars system, you are converting that environment from an anaerobic environment to an aerobic environment. And that happens pretty quickly. And it happens quickly because the bugs, the heterotrophic bacteria that are anaerobically breaking down the sludge get converted from their anaerobic mode to an aerobic mode. And that happens very, very quickly because those bugs can switch over. So there might be where you're seeing some odor initially when you turn the Mars system on, maybe 24, 48, maybe 36 hours, depending on how much sludge you have, because you are mixing some of that sludge up. But once you establish an aerobic environment within the lagoon, it'll typically, dissipate within a relatively short period of time. Somebody's asking about it, fixing the Mars unit. How do you fix the Mars unit to the lagoon floor, and do you have issues with floating? So the unit itself doesn't actually get fixed to the lagoon floor. It's got weight built into it, and so the weight is heavy enough to keep it in place. We do not see issues with floating units. We've probably got 2,000 in the field now, Mars units, and the only time when we see issues with floating units is when the operator pushes too much air above the maximum capacity of the airflow of the unit. It doesn't blow up when you do that, it doesn't break. It just causes the membranes to balloon. So if, for example, we can put up to 100 CFM through the unit, but if you start putting 120 to 150 plus CFM through a Mars unit, it's going to balloon the fine bubble EPDM membranes, and it's going to cause some floating to occur. And so in some cases that happens because the operator is unwittingly turning on the extra blower. In most of the cases, what we're doing is we're designing our control panels such that both blowers cannot be operated simultaneously. So overwhelmingly, the answer is no, the Mars units do not float, with the caveat of if you put too much air through them, if you far exceed the maximum airflow capacity of the unit, there's a possibility that it will. Mike Davis said, asked what our thoughts are on adding microbes to help reduce sludge. I think adding microbes can help. Microbes by themselves are, without adequate mixing within the water column, are only going to be so good, is what happens, right? Again, if the sludge is just sitting there and you don't have mixing and you're not getting oxygen to it, and you can put as many bugs in there in the water as you want, the sludge a little bit faster, but ultimately it's going to be limited in its success of what it can do because it needs mixing and ultimately to break down sludge. Now, if you've got an aeration system and you want to add microbes, it's very possible that you can get really good breakdown of sludge. However, what I would say is there are a lot of snake oil salesmen out there. There are a lot of companies that make bacteria and sell it for sludge reduction that really don't know what they're doing. That may give you a product that's either watered down in the worst case scenario, or give you a product with a super, super high bug count, but by the time they get into your wastewater and they actually, they don't have the nutrients they need within their existing, the wastewater, they'll actually die. So you'll see a significant die-off. We work with a company called Aquafix. Aquafix are out of Madison, Wisconsin. We're doing a video case study on them coming up in one of our future Lagoons Do Better TV episodes, which talks about the nuances of different bacteria. So it's really, really good. They seem to be a bit more top of their game, and we've used their stuff in the past in our systems and seen some really good success with sludge reduction. So it can certainly help, but it ain't going to replace mixing and aerating. You need that, and if you really want to get after sludge, you want to mix and aerate it, and you can add bugs too, as long as you get the right bugs when you do it. Okay, last question here. Is there any time when you would want to run part of the lagoon anaerobically versus aerobically? That's a good question. So there's a couple different answers to that question. Number one is if you have an anaerobic lagoon, if you have what we call a facultative lagoon, which is a non-aerated lagoon right now, and it's working for you, then great. I wouldn't advise adding aeration as long as it's meeting your limits. But this is a webinar not on facultative lagoons, but aerated lagoons. So the time when you might want to use some anaerobic digestion is if you're trying to get some nitrate removal, then having an anoxic or anaerobic zone within a lagoon can be quite helpful. The thing about nitrate removal is you need to do what's called a denitrification process. And denitrification actually can occur with the same bugs that eat BOD, but they need to be in lower dissolved oxygen conditions. So one of the things that we are actually looking to test right now, we're actually looking for some pilot facilities to test this, is taking some of our fully nitrified water from the back end of a lagoon system and recirculating it to the front end of the lagoon, where we're looking to get an anaerobic environment in order to get denitrification. And the reason we want to do it at the front end of the lagoon is that we need BOD as a carbon source for the denitrifying bacteria, in addition to low dissolved oxygen conditions in order to get denitrification. And if we can lower the overall level of nitrates, then that lowers the overall total nitrogen factor. That would be one of the reasons we would want to use denitrification with the lagoon. So if you guys have any questions, I'm going to wrap up the webinar right now. If you got any further questions, do feel free to give me a call. I will be around for the rest of the day, and I'll put my number in here into the chat box. And you can give us a call on the office phone. I'll be happy to answer any questions you have further. We do have some more webinars coming up. I think our next one is on lagoon nitrification. So if you're interested in that, specifically cold weather nitrification, but nitrification in general in the lagoon system, that should be a really, really good one. Thanks for joining us today. This was hugely popular, so we're definitely going to try and keep this going. If you do have a project you're working on or an application you're looking at aeration for, feel free to give us a call. We provide a completely free consultation in terms of doing aeration calculations. We'd love to help you out. This is what we do every day, and we really want to make sure lagoons are performing the best that they can, that lagoons do it better. So thanks a lot, guys, and thanks for joining us, and I'll see you later.